Thanks for the organizer for giving me the opportunity to speak here. So I will speak about some recent work on Brown measure. There has been some good progress on Brown measure formulas last 5 years or so. In this talk, I will try to highlight some main ingredients that for the approach I use, which is based on many earlier work of Hamilton reduction method uses by many people. For example, Harvard Schultz, they use this idea, this approach explicitly in the new proof for a Brown measure for RDEC operators. So Blinsky, Shinyadi, and Specher, they make a very good summary about this method. Then on the physics side, there are some other papers, like for example, Feinberg Z and Novak and his team a series papers on this direction. So let me first remind you that what is a Brown measure. So let me start with a matrix, n by n matrix. Yeah, so in this case, the Brown measure is just the eigenvalue distribution. One can recover this eigenvalue distribution from analysis. So if you look at the characteristic function, then take the absolute value, then take a logarithm. Then what you have is the summation of logarithm, and this is a subharmonic function. When you take the distribution of Laplacian, you will recover mu a. So in this case, you have mu a is just the distribution Laplacian of log determinant. Okay. And this absolute value of determinant is also equal to determinant of the absolute value. So this is the Brown measure for the matrix. Then about 40 years ago, Larry Brown, he makes sense of this Brown measure for any operator in finite quantum algebra. So now I have a phi. So this is a non-commutative probability space. Let's take any x in A, then one can, so this x is not necessarily a joint. One can actually associate a probability measure, which will generalize this approach. So you first look at so this is a work of Brown. Okay, so you look at the logarithm of the Fourier-Skeizern determinant, so which is equal to the trace of log lambda minus a minus x. Okay. Then this he showed that this is a subharmonic function. So if you take the distribution of Laplacian, you get a positive measure. And then the Brown measure is defined as the distribution of Laplacian of this. So which is exactly the analog of that analysis. Okay. And in addition, like this actually like this logarithm is equal to exactly the logarithmic potential of this complex measure. So the interest here is that to find some formula, a nice formula for large family of operators, so we can calculate the Brown measure. Historically, the interest for this is 20 years ago, maybe around early 2000, there was amazing work on invariant subspaces problems like related to this Brown measure. And then like Professor Krasko built this connection between reprobability and random matrix theory. And when we have some information about the operator from algebra, we can this often give us some prediction of limit measure of random matrix models. Okay, so it's actually interesting to know some information about that. So what I mean that we calculate the Brown measure means that okay, so we don't maybe take this definition directly. You want to have some formula, and this formula is tractable. You can get some information out of that. So it's actually easier to work on regularization. Okay, so if you look at what is regularization, so let's look at the first regularized determinant. Okay, so regularized determinant is log of x star x, take the trace, 1/2 of this, plus epsilon square. So I regularize by this parameter epsilon. So this epsilon is positive. Of course, that when epsilon is equal to 0, this will give you like the Foucault-Kaiser determinant. Okay, so it turned out that for this one, okay, so if you take the distribution Laplacian, you will also have a probability measure. And this is the object that is easier to work on. So in this case, let's see that if here is something that we should have, like let's denote this. Okay, so let's first calculate the derivative of this guy. Okay, with respect to epsilon. With respect to epsilon, so take the derivative for this with respect to epsilon. I have epsilon trace of the inverse. Take the derivative with respect to lambda. This is the first step to calculate the derivative. You get okay, so let us take a trace of lambda minus x star. Okay. So this is the regularized version. Okay, so why this is easier to calculate? So the general strategy here is to use Hermitian reduction. Okay. So meaning that okay, so you look at the 2x2 matrix of this. So this is safe joint matrix. But so free probability has a theory to study that operator value object. That here this is a Hermitian operator. Okay, if I work out like this Cauchy transform, so this B is a 2x2 matrix in the matrix value alpha plane. Okay, so the Cauchy transform, you will see that is exactly connected to this one. So gx of B is expectation of B minus X inverse. So in this case, is expectation of epsilon lambda minus X, lambda minus X star epsilon. Okay. So the thing is that if you look at this 2x2 matrix, let's look at the first. Let me denote this as Gij. Okay, so this is 2 by 2 matrix. Then at this, let's first look at the 1, 1 entry. The 1, 1 entry of this is equal to minus I epsilon, trace of lambda minus x, okay, plus epsilon square inverse. So this is like a kind of determinant, and this is I epsilon. So if you take the inverse of this 2 by 2 matrix, 1, 1 entry, give you this. And you can see that this is exactly up to this constant minus I is same as this derivative with respect to epsilon. Okay? If you look at the 2, 1 entry, so this is equal to trace of lambda minus x star, lambda minus x star plus epsilon square inverse. This actually is related to the derivative, first derivative with respect to lambda. Okay? So if I take a derivative for epsilon square, I have this inverse, right? So 2 epsilon, so let's cancel the have this. Now if I take a derivative with because this is the complex derivative, right? So here I have lambda bar. If I take a lambda bar, then take a derivative with respect to lambda, I get 0. Bar is a trace of the lambda. Yeah, Laplacian. Right. Yeah. Yeah. Right. So you can see that, okay, so if I continue to take the derivative for this 2, 1 entry, okay, so you actually get the regularized parameter. Okay? Yes, I take the inverse before. Right. Thank you. Right. Yes. So this is 2 by 2 matrix value Cauchy transform. So yes. Oh, right. So this is defined as this one. Okay. So this is my definition. Thank you. Lambda. Here you have lambda. So it's a subharmonic function defined on the complex plane. Yes. Right. So it's a generalization of this calculation. So if you take a distribution of Laplacian of local potential, you can recover the measure. Okay. So here, like you don't have a local potential from the beginning, but you have a subharmonic function. You take a distribution Laplacian, you get a measure. Yes. Yes, you are right. So it's a distribution of Laplacian. But in this case, I mean, if you regularize that, you can take a usual derivative. Okay, thanks. Thanks for clarifying. Yeah. So now you can see that clearly that it's useful to study this 2 by 2 matrix value Cauchy transform. Okay, but then the problem is that you don't want to keep doing this, that you want to use the tools from free probability so that you can get a different version of that. So that's what I want to talk about. So here, basically, here is some observation is the following. So if I look at this 1 entry, yeah? So 1 entry, so is equal to negative I epsilon trace of lambda minus x star lambda minus x plus epsilon square inverse. I want to say that this actually is a Cauchy transform, scalar value Cauchy transform. So it's equal to my claim is equal to Cauchy transform of this guy lambda minus x valued at x. So what is a mu tilde? Let me explain. So if I have a mu, that is a probability measure. On real line. Let's look at the symmetrization. So symmetrization is just the symmetrization of this probability measure. Okay. Now let's take a symmetric probability measure. So if mu is equal to mu tilde, okay, I take the Cauchy transform valued at I epsilon. So this is just equal to the integration I epsilon minus d mu of t. Okay. Now because of the symmetry, actually this will give you minus I epsilon integration epsilon square plus t square d mu of t. Okay. So if this is a symmetric measure, then that you can see that this Cauchy transform value at the I epsilon give you this. In particular, that means that this G11 is the Cauchy transform of this symmetrization of lambda minus x valued at the I epsilon. And so this is very small observation, but it's very useful. So why this is useful? Because it actually give us connection from matrix value sublimation, matrix value Cauchy transform to this scalar value Cauchy transform. For this scalar value Cauchy transform, we have much more tools that's available. Okay, so let me give you like a concrete example to demonstrate this observation. So this observation actually was used by Hagwab in the 2007 paper. I'm sure like it's also used in other places, but that's a place I learned. Okay. Now let me work on concrete example. So my example is as I look at x plus y, so my example is x equal to 0, y is equal to circular. Okay. So we know that the Brown measure of Vy is the uniform measure of the unit disk. Okay, so in this case we have so the thing is that this R transform this Y, okay, is operator value semicircular element. Okay, so what it means that is that if you look at R transform, so this actually is equal to this one. So this means that only the second free equivalent potentially they are non-zero. Okay? Other than that, the free equivalence is equal to 0. So this R transform has a very simple form. The consequence of this is that if you look at the definition, so R transform, so this is equal to inverse Cauchy transform minus B inverse. If I replace this B by Cauchy transform, what we have is this one. So this is equal to B minus gy of B. Okay. While this is useful, okay, you actually get a fixed point equation. Inverse, yes. Thank you. Thank you. The consequence of this is a fixed point equation. Okay, so therefore we have gy of B is equal to B minus this composition inverse. Okay? And while this thing has a very simple form, so in general this R transform is not defined everywhere. Not defined for any B in the upper half plane. But in this case, it's defined for any B in the upper half plane. So that this is true actually for any B in the matrix value upper half plane, meaning that the imaginary part of B is positive. Okay. Okay. If I denote, so this also has a very simple form. So if we do that calculation. So if I do that calculation, at least Ry of B, in particular, let's apply to this matrix. As very spatial form, this is equal to I epsilon, and this gives you 0. You just do the direct calculation. That's the product of y, b, and y, and y is letter matrix, where C is a circular operator, only like so then you will have this formula. Okay. So if I denote this matrix, okay, so if I denote this matrix as okay, so as I epsilon 0, now because of this particular form, Ry applied to this constituents form, this off diagonal term is 0. So therefore here I have a lambda bar inverse. Okay. And what is epsilon 0? Epsilon 0 is the 1-1 entry, so which has some contribution from 1-1 entry of this constituents form. Now, okay, so this gy of B is equal to gij, as I just denoted, and this is also equal to the inverse of this. Now let's do the comparison. Like we know that based on that observation, 1-1 entry actually is a scalar value constituents form. So that will give us the following. First, if I compare 1-1 entry, what we have is negative I epsilon. Left hand side is this one. Okay. Right hand side is minus I epsilon 0, then epsilon value square, epsilon 0 square inverse. Okay. So this is a constituents form, g mu theta lambda minus circular valued at I epsilon. And this is also a constituents form. So this is equal to g mu 1 valued at I epsilon 0. And in this case, mu 1 is the Bernoulli distribution. If I take mu 1 as a Bernoulli distribution, take a Cauchy transform value at I epsilon 0 give you this one. Why this is as I mentioned that this observation actually built a connection with a scalar valued Cauchy transform and therefore scalar value subordination function. So yes. Yeah, delta minus. Right, thank you. So because here lambda is here. Yeah. Yes, lambda is here. Mu1, yes, mu1 depends on lambda, right? So if I fix lambda, then this is right. Okay. So a consequence from Nika-Specher is that if you look at the symmetrization of this guy, you can actually write it as a free additive convolution of this mu1 with symmetrization of absolute value of circular operator. In this case, is a semicircular one. So actually, this result I use say that because that if you look at lambda minus c, you can actually because c is a R-diagonal operator, you can write it as high unitary times semicircular one, and you can move this one copy of high unitary to here. So therefore, you have high unitary times absolute lambda minus high unitary times circular or circular. Maybe I should have used different high unitary. So they are freely independent. So when you symmetrize that, a result of Nika-Specher says that when you do the addition of two R-diagonal operator, you can actually mimic this by adding two symmetrical polynomials. That's so a consequence of this is that you can write this symmetrization as a free additive convolution. Then this observation says that this I epsilon 0 from the beginning looks complicated, but actually it's just a scalar valued subordination function. And that is parameterized by lambda. Okay. So I say the conclusion is that this I epsilon 0 is actually the subordination function with respect to this first mu1 value at epsilon. But this subordination function actually is parameterized by lambda. Okay. And also, it also says that this subordination function, you have very explicit way to determine this epsilon 0. So once you have epsilon, once you have lambda, then epsilon 0 is determined. Now the next step, okay, so to calculate, let's say I want to calculate the regularized parameter of this circular operator. What we can do is that I can calculate the derivative. Okay, so I can calculate the derivative for 2-1 entry. Now with respect to lambda bar. But this 2-1 entry is also by that Cauchy transform formula, which is here, is also equal to lambda bar times lambda square plus epsilon 0 square inverse. Okay. Now you just do the implicit differential. Epsilon 0 depends on this lambda. You just do the implicit differential, you get a formula. So this is the version we get for regularized parameter. But how do we work on like the actual parameter? So if you want to calculate, let's say that you want to calculate mu x. I work on the boundary value of this substitution function. Meaning that I work on limit epsilon go to 0, omega 1 lambda epsilon. And in this case, you can actually identify some lambda exactly that this lambda is in the open unit disk. So that when you after you take a boundary, you can still do the implicit differential. And if you follow this strategy, you can calculate the Lagrange. Any questions so far? Okay, so this is a well-known example. Maybe use a slightly different angle to look at the calculation. Now I want to talk about how to generalize this approach that for additive model. Maybe first I could point out like a direct generalization of this approach is an answer to a question about Young and Lehner. So they ask the question, what is the Lagrange ratio of x plus y? So where this y is high unitary, not high unitary, R diagonal. Of course, like here, x, y, they are freely independent. Okay? So if I follow that strategy, I later use x to be this one. Capital Y is Hermitian reduction for Y. Okay. Now I look at the coefficient form. Value B. So you have subordination function. Y plus goes operator value subordination function. In this particular case, so here is a proposition. In this particular case, is y is R diagonal. You actually can prove that this subordination function has this form. So if you value that this 2x2 matrix, you will get I epsilon 0, some I epsilon 0. Here you have sen lambda. And this is because one way to think about it is that these two matrices actually they are free independent with respect to diagonal algebra in this case, because of y is R diagonal. Okay, then so if we can use this subordination function to help us to detect the information about the formation of x plus y. Okay, again, I want to focus on the case I work on regularized formation. So to calculate regularized formation. Okay, so actually I have to calculate the derivative with respect to lambda bar for 2-1 entry. And this 2-1 entry, if I apply that subordination relation, actually this can be written as the following. I take a 2-1 entry of right hand side. I give you trace of lambda minus x star, lambda minus x, lambda minus x star plus epsilon 0 square inverse. Okay, it's not epsilon 0 because I apply the subordination relation. I get epsilon 0. But now this epsilon 0 is again a scalar valued subordination function. So epsilon 0 is equal to, so I epsilon 0 is equal to subordination function valued at I epsilon. So where this subordination function is different, so I choose the thing is that for the left hand side, I have Cauchy transform of x plus y minus lambda valued at I epsilon. So this is 1 entry. On right hand side, you have Cauchy transform of so Cauchy transform symmetrization. Okay, right hand side is symmetrization of x minus lambda I epsilon 0. Okay, I epsilon 0. And my mu1 is a symmetrization of x minus lambda. Mu2 is a symmetrization of y. So these are pretty much like arbitrary two symmetrical probability measures. So when you consider this, okay, so I have a scalar value subordination function valued at epsilon, you get epsilon 0. So you get a family of subordination functions. They are parameterized by lambda. And this will allow us to do the implicit differential. Because like here, epsilon 0 also is a function of lambda. This will give you the sound density formula. In particular, if x is equal to 0, then this will recover the Brown ratio for Brown ratio of R diagonal operator, result of Hagoub-Larsen and Hagoub-Schulz. Now, next I want to talk about another direction. Is that I look at x plus another case. Is that x so y is circular or y is elliptic. So elliptic operator is interpolation of circular operator and a semicircular one. So you can just write it as alpha s1 plus I beta s of 2. So here alpha square plus beta square is equal to 1, and s1, s2, they are free semicircular. In particular, if alpha is equal to 1, beta is equal to 0, this is semicircular one. So we can calculate x plus y. Okay. So to explain that this the result, let me first remind you that the Brown measure of circular operator. So here is example of the phenomenon. Okay, so I look at okay, so x is equal to 0, y is equal to circular. Then at the Brown measure of circular is the uniform measure supported on the unit disk. So the other case, x is equal to 0, y is semicircular. It's semicircular. Okay, so then this is a safe joint operator. The spectral measure is a semicircular distribution. What's the connection? So this is average. This is a uniform measure supported on unit disk. Okay, and here this is a semicircular distribution. Here's the connection. If I look at take here as x, if I take the integration along this y coordinate, okay, so this height is square root of 1 minus x squared. Here, if I look at the corresponding part, I look at 2x. The density here, after constant, is square root of 4 minus 2x squared. And you can see that these two are equal to each other. So even though they are completely different measure, but they actually have a quite direct connection. So now I want to say that this actually is a very special case of a general phenomenon, which is called, which we can call maybe model deformation phenomenon. Yeah. Okay. So this here I compare Brown measure of x plus circular. The other case is Brown measure of x plus elliptic operator. In particular, you can think you take addition with a semicircular one. So it turned out like there's a canonical push forward map, so that this one is a push forward measure of this one. Okay, so here's the theorem. So this is mu of x plus g. If I want to calculate the measure, so this is equal to the push forward measure of this. So where this phi is a map from complex plane to complex plane, it's surjective map. And it's pretty nice, and it's explicitly constructed. In particular, if my x is equal to 0, g is a semicircular one, then let this phi give us that map. Yes, this. Here x. Yes, depends on x, right? Depends on x. So if I fix x, then there's a unique canonical choice of this push-forward map. Okay. So this was first observed by, okay, in my paper with Qingwei Hall, and then Hall with Qingwei for the special case that x equal to x star. For the general case, I use so for these two work, they use the PD method to derive this result. Then there's a free probability method to obtain this. So let me describe you like what is this push forward map is about. Now why this appears. So any other questions so far? So example, I compare x is a safe joint. Okay, this G is semicircular. Let's say that my semicircular one, so this is mu of x plus semicircular one. So this is safe joint operator. The spectral measure, there are some paths in the real line. Then there's a subordination function. Subordination function correspond to this free additive convolution. So this will map this this part to some pictures like this. Then what is the Brown measure for x plus circular? Is actually the following. I look at is symmetrical with respect to x axis in the Brown measure of x plus circular is actually supported in this picture. And what is a push forward map? So what is push forward map? So this phi is actually equal to the inverse of that subordination function. So this is the very particular case for this x equal to x star safe joint case. If x is not safe joint, then there's a generalization of about this map. I can say a few words about why like there is such map. So now my case is y is like elliptic, so it's alpha x1 plus I beta s of 2 alpha square beta square is equal to 1. If I look at this y, so this y is a generalization of the case 0 circular circular star 0. So this is again matrix value, operator value, semicircular element. Meaning that the R transform has very explicit form, so this is given by this one. If you apply to the matrix of I epsilon lambda bar, you get something like this. Here gamma of lambda, gamma bar of lambda epsilon. Okay, so where this gamma, what is gamma? So where this gamma is the expectation of y. It's kind of covariance of this y. So why that there is a push forward map like that? Again, I look at the operator value I transform. Okay, operator value I transform. So here, my y is elliptic. In this case, the consequence is that this subordination function has a very explicit formula. So this is given by b minus y of this one. So you can see that from R transform. Okay. If I replace this R transform by the definition, so g of x plus y inverse, so this is equal to g of x inverse plus y. Okay. Now I plug like the g of x plus the Cauchy transform of x plus y. What you obtain is b is equal to, and this actually is subordination function, and the other part is this. If I choose my parameter nicely, if my parameter gamma is equal to 0, sorry. B has an inverse. Last time, you mean here? Oh, you're right. Thank you. Yes. Thank you. So this subordination function has a very explicit formula. It's kind of linear of this operator value equation transform. If my gamma is equal to 0, that is circular case. If gamma is different from 0, then that you can see that there's some relation, meaning that this subordination function, it will give you something like okay, will give you I epsilon, but not lambda anymore, but you have some z, and this z is exactly related to that push forward map. And actually, this is this push forward property not just true for the Brown measure. Actually, it is true for the regularized version. For the regularized version, you also have this regularized map, so that this regularized version also have this push forward property. And the good thing for this is that if you regularize that, then this map, this phi map, is homomorphism of a complex plane. But in general, when I take a limit epsilon go to 0, this is the limit of a family of homomorphisms. So let's maybe give a little explanation about why this push forward property exists. Maybe I should say that there is also multiplicative version of this phenomenon, which relates limit operator Brownian motions on unitary group and Brownian motion on general linear groups. At least that part was done mainly by, at this time, is done by only by PDE method. I think it's challenging question if one can use the free probability method also get a proof for the multiple version of this model deformation with that. Okay, so I think I should stop here. Thank you.